Hello, everybody. Good morning, good evening, good afternoon, and thank you happy 2024. I guess I should also include to this one. Hi, Jesus. How's it going?
It's going very, very well. Thank you.
That's
Happy
good.
24 to you too.
Thank you
Good
very
to see
much.
you.
Yeah, good to see you too. It's been a while. I must say I'm just re-emerging out of this time, between Christmas and New Year. What
Oh,
day is it actually? so, but yeah, it's been good, and I'm happy to do this very first live stream of the year with you together, Jesus. So
yeah.
thank you for
Yeah, I know we kind of discussed whether it would be a bit too early in the year. So I'm sure we're catching someone still with one leg in vacation, one leg coming back. But
yeah yeah.
yeah, what better thing to do, even if you're on vacation, to watch an episode of Going Meta, right?
Yeah, totally. I mean, just a little service update. It's Thursday today, the 4th of January. So just in case
That's
you're
right.
wondering.
That's right. Just another variation. I mean, but we
Yeah.
still are the webcast that runs on the first Tuesday of the month, right? With
Yeah,
some minor exceptions. I mean, the
yeah,
Tuesday would have been a bit, really, really too early in the year, right?
yeah. That would have been a tough sell, I think. But yeah,
Exactly.
today, the 4th. So I'm hoping everybody had a good New Year's, had some nice days off if you had them, or if you worked through it all, then obviously welcome nevertheless to today's episode. It's already episode 24, so we are well into the higher numbers now almost, and we have yet another topic. It's like a little mini series within the series, I would say. So I think let me
It is.
quickly look at this.
Yeah, the thing is,
We
it's
started
so
20.
rich
Yeah,
and
yeah,
so timely that it's difficult to get out of it, right? So I'm
yeah.
sure we'll take a break, but we're kind of connecting it to something we had done in the past, right? So we're staying on the topic of knowledge graphs and LLMs and RAG, but we're connecting it to ontologies and to kind of the essence of our series, right? And we're going to hopefully go meta today. So we're again building on what we've done over the last 2-3 episodes, and bringing in some additional elements. So that's the plan today.
Sounds good. Sounds great. I'm looking forward to it. If you haven't watched the previous episodes, don't worry. Everything is on our overview page. If you click on YouTube, you find the playlist there as well. I'll post a link in the chat in a second, so you can catch up on the episodes of the past. But you don't really have to. It's you know you have to, obviously, but you don't have to do it now. You can stick around, and you can watch this one. We, as Jesus said, I think we gonna tie it together a little bit to the previous ones, obviously, but it's still I think it should be okay. What
Sure.
you
Yeah.
think?
No,
Yeah.
I'll open with a brief recap of the previous episode, and yeah, like you say, anyone who wants to dive deeper, all the assets, all the recordings are available. So feel free to go and consume them at a time that works for you. Should I? Actually, I'm going to share my desktop.
Yeah.
And as usual, let me do my entire screen here. Share. Let me know when you can see it. And actually, quite conveniently, because it's after choosing and preparing the session for today, I got this, I got tagged in this note by Dan, and on something that Jason had shared today, and it's this time of the year when everyone publishes the predictions for the year, right?
Yes.
It was very interesting, right? Because it's totally the topic that we've been working on for the last few episodes and that we're talking about today, right? And one of the predictions, and it's actually the one that Jason mentions, is all about how RAG will evolve from semantic, as in vector search, to something richer, to something like based on graph networks, right? A lot of what we've been doing. So it was another, confirmation of what we're doing is perceived as really something that's valuable, and it's the direction that this space is going to take. So it was quite nice to get that note from both Jason and Dan. So
Nice.
but Yeah, I was going to say that as usual, I'm going to open with a couple of slides to set the context and then jump into some code. So I hope it's all visible and readable. But yeah, the idea is talk about still RAG, still integration of knowledge graphs and large language models, but we're bringing in ontologies. And let me explain how that happens. Again, 2 minutes on what we've been doing. So it's all about RAG. I mean, for those who have been who have missed the previous episodes or have been living under a rock, RAG is this pattern, this architectural approach, if you want, of this integration that, for interacting with large language models that involves an external source of information, right? So we know that large language models are great at their creative generative capabilities, the language capabilities. They can do analogies, they can do reasoning, they can do generalizations, they can generate language. But sometimes the knowledge of the world is limited, and it is even more limited in your enterprise-specific knowledge, right? So they've not been trained on that. So we have to inject that knowledge somehow, and RAG is the kind of most widely accepted approach to do that. So when we ask a question to an LLM, first we go out to an external source, Neo4j knowledge graph in this case. We retrieve all the information that we believe, that we think it's going to be relevant to answer our question, and we pass it to the LLM as context so that the answer generated is based on this information. So we kind of take control over that. And that's the idea of RAG. I mean, like I said, we've been talking about it for weeks, so I won't spend much more time on it. What was interesting is recently in the last episode, we focused on what we call advanced RAG patterns. And these are the ones that actually combine two elements. One is, basically the two types of semantic search, vector search and graph-based search. And it really, when it becomes interesting, right, when you can combine the two. And in an attempt at explaining how that works, I've created these visual, which I hope is going to be useful for these. So we have a knowledge graph, right? A knowledge graph that captures information about your organization, about your problem, about your domain, right? And your knowledge graph will contain nodes and relationships, obviously. But some of these nodes will contain properties that may be fragments of texts. Maybe because that's human generated, human entered information. Maybe because it's the result of parsing unstructured documents. There can be many reasons, but there might be fragments of natural language in there. And we want to make use of that. And the best way to process and to do semantic search on natural language is to create embeddings and index them in a vector index. So the way I see that is somehow like a projection of these nodes in a different search space. I mean, I put it like a plane there. It's not a plane because it's multidimensional. I mean, we cannot even draw it. But the idea is we pick some of the information in these nodes, we vectorize it, and we project it over a different search space, which is this vector search space. And what we can do there is we have, like, let's say a question or a string or an image or an audio, whatever element, and we can do a vector-based search that basically will scan the index and return some results. So when we do a search, we find some. I mean, search is based on distance, right? On this distance in a vector space. So that will be typically Euclidean distance, cosine distance. But the idea is that you find the closest vectors to the one that your search element, right? And for those vectors, what we're going to do is we have to get back to the graph because these vectors are stored in nodes. And that's where we do this kind of second step where we enrich the results. So we not only stay in this vector search, but once we have the vectors, we navigate back to the graph, and we can expand. We can, because we're aware of the structure in the graph, we can enrich these results. And keep in mind that all this process of going to the vector search, to the vector index, and navigating the graph is what happens in this intermediate step in the RAG interaction. So we are in the process of retrieving all the information that's potentially relevant to answer a question or to generate some content or to provide an answer to something. And that's the information that I'm going to pass to the LLM. So I'm interested in having the highest precision and the highest accuracy in this information. So I want to make sure that I combine in the most powerful way this vector search with the graph search, and that's what we've been doing. I don't know if this sort of visual helps or confuses more, but that was my attempt at describing what we've been doing before we go into the code, right? So
yeah, no, I think it's helpful.
retrieval.
It's helpful. Yeah, I think it's helpful. It's always, especially with, I mean, you notice we talk about the graph space since many years now, and I think we come at a time where people understand when we talk about graph, we don't talk about charts. So at some point, people understand this. Now we bring in the vector comes around. It's like a completely new concept for many people. It's again very very abstract, very unlike graphs, very abstract, very very difficult to grasp what it is. And then I think this is a good visual to understand. Okay, there's the graph, there's the vector, there's the points in this
Exactly.
crazy grid, and then combining
and
it.
somehow that also explains these kind of prediction. I mean, it's not a prediction because it's more a reality than anything else that we saw on LinkedIn before. So yeah, you could get some valid results with just vector search, but you would only be doing half of the job, right? So you could deal with the simplest cases where you kind of just chunk unstructured data and you put it in a vector. But when you combine the two is when you can be really precise, really rich, and really accurate. And that's what we're going to be. I mean, we've shown it in the past, and we're going to reiterate that idea in today's episode. So that's RAG. That's what we call advanced RAG, because it combines vector search with graph exploration. And the example that we used in last episode was, if you remember, that of it was a legal document. It was like some legislation from Ireland where we have just a PDF, right, or even an HTML version, but it was a text document. There was no structure. I mean, there was some structure in it because the document has kind of parts, and the parts had sections, and the sections had definitions. So what we did, and I'm not going to go into that today, is kind of try to create a graph representation that somehow captures the structure of these documents, and that's what we did. And the thing is, once we have it in the graph, this graph reflects this idea, right? So we have the legislation, as you can see, the orange node. This is just one of the paths that takes you to one of the definitions. But it would be a kind of a tree. There will be multiple of those in the document. So you have the legislation with parts, with sections, definitions, and clauses inside a definition. And the thing is, while breaking down in small chunks is good in a way, because it will give you much higher precision when you do vector search, sometimes it can be a problem, because if you get just a portion of a definition, let's say you have a high match, a high proximity on a vector search on this portion, you might use these as the relevant fragment of information for your answer. But the interesting thing is that this should be taken into context, and this is only a clause inside a bigger definition. And this idea would be lost if we don't do the graph exploration. And that's exactly what we did last time. And the way we did it, and you can also look at the slides from previous episode, was by we use LangChain, right? We're going to go into the code. We're going to use Python, and LangChain is super convenient to kind of orchestrate the interaction with the knowledge graph and with the LLM. And basically what we did is we have this kind of vector index handler where we can do vector search, and it had this additional parameter, which was the retrieval query, where we could inject any random cipher. Cipher is a query language for Neo4j, of course, that would basically implement this navigation in the graph that we saw visually before. So to the results of your vector search, when you do a vector search on this handler, every node return, every match return, you would apply this contextualizing query. So you would run a cipher on each of the results. And that's it. So that was what we did. And that was great. It's super powerful, but it had some limitations. And I mark it there. So it's a bit rigid. Why? Because these queries had to be specific of your model. Remember? So of your model, of your graph, basically. So this cipher has to be prepared to explore, basically know the kind of information that this vector search is going to return, and based on these return nodes, know how to navigate that. And that's entirely graph dependent. And well, that can be acceptable. What we're going to be exploring today is how can we make this a bit more flexible, a bit more dynamic, and that's where ontologies come into play. Make sense?
Yeah, that sounds cool. Yeah,
limitation. And the idea is pretty simple because we've done it before. I mean, I put just a brief pause here just to, I mean, that's just the animation, but you probably remember in episode 15 where we built, again, it was another ontology driven, I mean, we call it semantic data app, but it was a Streamlit application that was entirely driven by an ontology. So the idea there was, okay, we're going to build an entirely generic Streamlit application that probably showed some elements in the graph, but there's no cipher hard-coded in there. So I cannot anticipate what the shape of my graph is going to be, what the schema of my graph is going to be. So my application, what it's going to do is it expects some ontology, some schema definition in the graphs on the graph side. We're going to read it, and this is going to drive the behavior of my application. And that's going to drive the kind of queries that I have to create. The idea, again, if you remember, was instead of having bigger and heavier application logic, which means a lot of code on this side, maybe thinner application logic and more information on the data side. So we put a bigger description in the graph, and we'll see that an ontology is also a graph. And my application is going to be dynamic, entirely dynamic. It's going to go read your ontology and drive its behavior from there. So that's what we did in this Streamlit application. And what we're going to be doing here is exactly the same. Basically, instead of giving you a hard-coded cipher query here, what I'm going to do is go read your graph, get the ontology, and based on the ontology that you share with me, I will derive the behavior that I want to implement. So it's going to be entirely dynamic and driven by what I put on the graph side using ontologies. Does it make sense?
Yeah, that makes lots of sense. Sounds good.
Perfect. Okay, so that was the idea in that episode, which I think it's kind of relevant for this one. And well, from there, let's go and see some code. So okay, as usual, I've created a sandbox that I will destroy at the end of this session. It's an empty one, and I'm going to be driving from this notebook. I hope you can. It's readable. Is it big enough, Alex? Is it?
Okay? Maybe I make it a little bigger.
Okay, let's try.
Yeah, I think that should be good.
I hope the text fits in the page. But well, initially we just import. I mean, we write in Python. We're going to be using LangChain, OpenAI. GPT as the LLM, and Neo4j as the knowledge graph for RAG. So here I'm just connecting. I've pasted the IP. So when this, of course, like always, is going to be available in the GitHub repo at the end of this session. And basically, what I do is, you know, that when you access your sandbox, you have all the connection details, user, password, and the URL. So I've copied these. And I'm here. These should be my credentials, so I can now connect from my code. So one of the things that I can do from LangChain is connect to the graph in a standard way, like using the driver and running some cipher against it. And I'm going to use that to populate the graph. And I'm going to rebuild the graph with the legislation that we used last session. So I'm connecting to my graph. I'm creating a Neo4j graph handler with my credentials, and I'm going to run these 3 steps, which basically import the legislation graph into my instance. So hopefully, in a second, here we go. We should see all the elements loaded here. Just as a way to check that everything looks as expected, we can run this query. And we should get the expected results. Basically, what I'm doing is I'm getting the path, the tree that gets from the root element, which is the legislation, all the way to the definition of the term unavailable deposit.
Can you zoom in here as well a little bit?
Let me make this a bit bigger.
Yeah, perfect.
So yeah, I'll show the cipher again. But basically what I'm doing is, okay, I follow, in this case, we created intentionally a pretty simple graph using just a contains relationship. That's something that that can be, you know, modeled in whichever way you prefer. And basically the idea of today's session is that there will be elements that change and that have different names in the graph. And we want to be able to have our RAG application dealing with those in a dynamic and flexible fashion. So basically I'm starting on a root that contains the asterisk is a variable number of hops. So there will be a chain of contains that take you all the way to a definition. And then the definition, I'm saying that is that of the term unavailable deposit. And the definition will have clauses, right? And these are the three last elements. So we can see here that the coloring reflects that. So the blue ones are clauses, the green is the definition, and the rest are sections and subsections inside the chain. So it looks like it's loaded correctly. So we have the tree that represents that that portion of the legislation. And then what we did here is, you probably remember, is we are going to vectorize some of the content. So if you remember, there is these definitions contain fragments of text, right? For example, this is a definition of a deposit that has some text and that we might want to run some vector search on it. So I'm going to take these definitions along with the term, and I'm going to vectorize that. My strategy to do that, and you can do it in many different ways. I mean, because when you use LangChain here, what you have to pass is a node label, so which node types you want to embed and which of their properties. So you specify an enumeration of the properties that contain a text that you want to embed. You want to vectorize an index. So my strategy here, because there are nodes of different types, because we have, like we saw, we have definitions, we have clauses, we have all the types of elements. The ones that I want embedded, I gave them an additional tag, which I call embeddable. So that's my way of, I added to the clauses, I added to the definitions, and to all the elements that contain some properties that I want embedded. And like this, it's easy. I mean, I have a secondary, an additional tag, an additional label that then I can use to say, go and get all the embeddable nodes, and in particular, these three properties, and go create the embeddings. So this is using the OpenAI embedding service. You can use your preferred one. So we're not prescriptive here. LangChain supports integration with the large majority of providers. So you can use Vertex, you can use Bedrock, you can use even local, you can use Olama if you have a local LLM. So there's many options there. So what this has done is that it has created a vector index that I've called vector index, not very original. And it's embedded these values. So if we go now to our graph and I do a schema, I should see a vector index, which is of type vector, that has been populated for vectors of type embeddable, right? And every node at the same time, you will see that I'm going to have to rerun this query to see, not this one, the previous one. And we will see that definitions now have not only the definition before or clauses, but also a representation, a vector representation of the embedding, right? And that has been persisted as a property. Good. Perfect. So we are all set to start running some queries. So back to our code. The first thing we're going to do is let's get a question, the one that we used last time. Let's get the first one. Our question is, what is an unavailable deposit, and how does it become unavailable? Right. That was exactly the definition that we saw a minute ago. Right. So we see that an unavailable deposit, that's the definition, means a deposit that is due, blah, 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 blah. And then it further defines it by saying it can be either, and there are three clauses, when the competent authority, blah, 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 when a court has made for reasons which are directly to that. I mean, an enumeration of clauses that further specify the definition of an unavailable deposit.
It would have been a couple of lines, paragraph lines, different paragraphs in the actual PDF.
Exactly.
Yeah.
But the point here is that you have to take the whole thing in
Yep.
context, because otherwise you would get just a fragment of it. And that's what we saw here, right? So if I take this question, I can do a vector search. So I have a vector handler now. That's what this created the vector, created the vectors, the embeddings, and populated the index. But it gives me a handler that I can use to run some queries. And here I'm doing a vector search. I'm doing a similarity search with the question that I've selected. And this returns a number of matches. So this is, if you, in the visual that we used before, we're in the projected space and we're finding the vectors, the fragments of text in our graph, in our legislation, that are closer to our question. And the question, remember, is what is an unavailable deposit and how does it become unavailable? And luckily enough, yeah, one of them is it refers to an unavailable deposit, right? But it it's fragments of them. Some might be closer, some might be incomplete. So there you go. So that's the kind of results when you do a vector search. Now, because these three components, these three clauses make sense in context and all together, what we need to do, before I go into that, we build this vector search in what's called a RAG chain, right? So we, LangChain gives us the possibility of creating a retrieval Q&A chain, which basically implements the RAG chain that we saw before. So it will go and do the vector search that we just saw here. And with the results, they will be passed to the LLM, and the LLM will return an answer. So basically, this orchestrates the whole process. So if I create this handler and run the question, it will tell us, in natural language, that the definition that mentions. That's interesting. Seems like it's taking I hadn't run this one. Did I not run that one? Oh, that makes a lot more sense. Unavailable deposit. Yeah, I think I didn't click on this one and it was getting the results from a previous execution. Anyway, when we have an unavailable deposit, the closest answers are, the definition of an unavailable deposit. But then there's the closest and some other fragments. Sorry, maybe people were a bit confused because the results were not making a lot of sense. But anyway, these are the vector results that match this search. And then when we run the whole chain, the RAG chain that does the vector search, passes it to the LLM, then what we get as an answer, there you go, is an unavailable deposit, refers to a deposit that it's due and playable. So it looks like it's picking something, right? Probably the first result, which is a good part of the definition, but we know that it's not complete. So that's the kind of experience that we're going to get if we go just with vector search. So that's exactly why we wanted to implement these advanced patterns. And that's what we're going to do. I mean, I'm not going to repeat exactly what we did last week, but what we did is we implemented, we search, and then we, on the results, we navigate to complete the picture and provide a consistent context. Now, what we're going to do is I'm going to define, this is a bit large. I don't know if I'm going to, it's not very large. It's just it's a function, a couple of functions. But basically what this function is going to do is it's going to generate dynamically the context query. Because further down, as we're going to see, I'm going to create this, as I showed in the slide, I'm going to create a contextualized vector store that is, again, another handler on the same vector store, but I will inject this retrieval query at the end. So I'm going to say, do the same thing that we've done before, but to your results, apply this contextualization. And this is not hard-coded anymore. This is going to be run dynamically. And this function, get dynamic context query for a particular pattern, is the function that I was showing here. And I'm going to try to go into in a bit of detail here. So the first thing, it's going to go and get the ontology from the graph. So in order to have that happen, and we see that there are resources, there are sub-property offs, we'll make sense of that in a minute, we need to have an ontology in the graph. And we don't have it at the moment. We only have the graph that we've created. So let's probably go and populate that. To do that, we're going to use, you can use your favorite ontology editor. I'm going to use Protege, which I've used in the past. That's the local, the desktop edition of the the web protege that we've used also in other episodes. And what I'm going to do is I'm going to basically annotate my ontology. So in my an ontology describes the content of a graph, right? It's kind of an explicit description of the graph. In a way, we get something close to an ontology when we do this db schema visualization. So if I do schema visualization, wow, that's not very good. I mean, that's why an ontology is much better. I mean, what we're doing here, and yeah, that makes sense because of my use of the related to and the contains relationship. So essentially, we have this is a clause, this is the legislation. So this shows the different entities in my graph, and then the possible relationships between them. This is, of course, not formally described by anyone. This is just learned from the graph. And because we use the same two relationships, related to and contains, you will find them across every possible pair of nodes, which is a bit confusing and not very helpful in this case. So here's where you will probably want to create a real ontology with a formal definition. I mean, pretty much the same thing, which are the entities and how they relate to each other, and eventually annotate them as well, which is what's going to be useful for us. So let's do that. So I go back to Protege, and I'm going to say, okay, I'll create my ontology, and I'm going to give it a URI. For example, I'm going to call it going meta live, and this is my ontology. Let's call it, it's going meta 24, and this is the legislation. Whatever, I mean, you just pick a name. For example, this one. And I'm going to import an ontology, and I've put it here because I've created a common ontology for RAG patterns that just defines a couple of patterns that I've implemented. These are the ones that I've implemented. So these will be extended, of course. This is a turtle definition, but basically it describes there's a further detailed relationship. So I'm going to describe that there are some relationships in my graph that are useful to provide further details. That's the idea of the definition before. So when you have a definition, the definition can have sub-clauses. So this relationship, whatever it's called, contains in my graph, but it could be called whatever you want in yours. I'm going to annotate it and say, this is a relationship that is of type further detailed relationship. Because these relationships are the ones that my RAG application are going to take to use and expand the result. So that's what I try to describe here. Further detailed relationship is a relationship that connects an entity to related entities that provide further details about it, right? I'm also defining another one, which is the one that goes backwards. It can be seen as a synonym. I don't know if it's exactly the same. Is this readable? Should I make it a bit bigger? But I call it inverse contextualizing relationship. So what happens if I get a portion of a relationship, a portion of a definition or a portion of a document? Sometimes I want to put it in context and I want to navigate to the parent. And that's what I think Thomas Brattanich and others have called the parent pattern. So it's a way of going to a container and then retrieve all the siblings to get not only the exact match to your vector search, but all the additional elements that are connected to the same parent. So it's a way of bringing, again, additional context that's potentially relevant as for the LLM to generate the answer. So these are the two relationships that I've defined. And I've implemented the associated behavior in my RAG application. So these are the two. And I'm going to import these ontology in Protege because I'm going to extend it. So I can import ontologies here. I'm going to say that I am going to import an ontology that's located on the web. And I have I've added a bookmark here. So this is my ontology. Again, all this is public and we'll add it to the repository. But if I continue, it will import it, finish, and it's all done. So this ontology has been imported. And now, if we go to my entity view, there's no classes defined. That's what I'm going to do now. And there's no object properties. Well, there's the two that we defined. There's the further detailed relationship and the inverse contextualization relationship. Okay, so let's create a class. For example, if we go to our graph, you probably remember that there were definitions, and definitions contain clauses. The way to represent these in an ontology would be something like, okay, there is a class. I'm going to add a subclass that is going to be called a definition. Good. So I create this entity, and there's another entity which is a clause. I'm not going to create the whole ontology, but you see what I'm going. And we've done this in other episodes. I believe in this one with Streamlit. So you have the whole creation of the ontology. But basically, you describe the entities in the types of nodes in your graph, and then you can define the relationships between them. And in particular here, I'm going to create the relationship that exists between these two, which is called contains. It happens to be the same across all the graph. It's probably not the case in any other real graph. We've called it like that here.
Hopefully not.
In particular here, let's go back to my project. Contains is a let's call it is an object property. An object property is a relationship. I mean, in RDF, in OWL, which is the language that we're using here, there's the definition between object properties and data type properties. In a Neo4j graph, in a property graph, an object property is a relationship, and a data type property is an attribute. There's a property of a node. So basically, those that have a literal value, that can be a numeric, a string, a boolean, an array. So in this case, we're defining the relationship contains. So contains is a relationship, but and it's also a relationship. We can say that it has a domain and a range. You probably remember that domain and range is the definition of what entities does it connect. So the domain of this relationship will be, it starts from a definition and it ends, the range ends in a clause. Okay? So basically what we're saying is that the contains relationship, it's not entirely true because we're using it for other cases. But in this, the fragment that I'm interested in is the one that connects a definition to the clause. And I want to specify that my contains relationship is a further detailed relationship, is a relationship that actually I want my RAG to use to further specify, to further contextualize the results of the vector search. So that my way of specifying that is saying that this is a subproperty of further detailed relationship. So if I do that, it will naturally put it in the hierarchy under its parent. And that's, I mean, I'll stop here. That's enough for me for now. But you see how we could define the elements in my ontology and annotate them. So what I've done here is I've said, okay, there is a relationship called contains that connects definitions to clauses. And this relationship is very particular because it's a further detailed relationship according to the RAG ontology. What my RAG general purpose engine is going to do is going to go and find that there is a further relationship existing in my ontology, and it's going to generate cipher based on that. So let's first save this. So if I do file, save, and we're going to choose, I mean, we could pick any syntax. I like Turtle. I think it's particularly readable. So if I save this, I'm going to give it a name. For example, I don't know, something like going meta 24 onto legislation. And I save it locally. Perfect. And now I'm going to show you what that looks like. Now it's in my local drive. And this legislation, if I open it with my, I don't know, text editor, it looks something like this. Let's make it a bit bigger. And again, I don't want to go into the details of this syntax, but you see the elements defined. So we've defined, I mean, we've created an ontology, right? That imports the RAG ontology, which is a public one that we have created, but it's public. And it defines one object property. The property is contains, and it's an object property that's a sub-property of a further detailed relationship. And it's a property that connects a definition, the domain is a definition, and the range is a clause, which are themselves classes. So this is all, right? So we have an ontology definition. It took us 2 minutes. It's a limited one, it's a small one. Now I'm going to put that in my graph because this is what my RAG application is going to go read. And based on that, it's going to build the relevant cipher. So how do I do that? Well, I can go to my graph and I can import ontologies using semantics. So it's I'm in the sandbox, so it's already installed. I can do something like call ntns onto import. Actually, before we import, let's preview. Let's see what it looks like. And actually, I mean, I could fetch it from a file, but I'm going to literally copy paste it and use the inline flavor of the method. So if I do that and say that it's turtle, all I'm going to do is, like I said, paste my ontology here. I'm literally copying it from the file that I just showed you, and boom, pasting the content here. So these ontology import, ontology preview, they have the two flavors. The fetch, where I can say, go read this file and take the content, and the file can be local, can be HTTP, can be FTP, whatever. Or I can just inline the ontology. And here what I've done, like I said, is I pasted the file that I just showed you. It's really copy paste, right?
Okay.
So I'm not loading it yet. I'm just previewing it. And if there's no errors here, that should show me, well, more or less what I was expecting, right? So it's there's a class, a relationship, right? As you can see, called contains. Let's make it a bit bigger. So contains is a relationship, you can see it here, that has a domain definition and a range clause, right? So it's a relationship that's established between definitions and clauses. And it's also a sub-property of, a sub-relationship of a standard one called further detailed relationship. So that's exactly what I wanted to do. Make sense?
So it tells me basically that this is part of a like graph, which is not a, how do you say, it's part of a tree, if you will, and then you can when you look at it, you should be looking also at the nodes and the relationship that come before it, so it knows it's not stuck on this individual point.
So this, in a way, this is kind of a separate graph. So once we import it, and we can run it right now because this is a preview. Let me run, instead of preview, let's run the import. So now we've loaded it. So there were 6 triples there. We've imported them, and they've been persisted in the graph. So now we have these loaded in our Neo4j instance. So we have it here persisted, and the contains, if we expand it, we have the domain and range. So you're right. This is a graph. Is another graph, but it's kind of a metadata graph. So it's kind of separated. We have our legislation with all our nodes and relationships, and separately we have a separate graph that describes my graph, right? My instance graph. So it's somehow as if I had persisted as nodes and relationship the result of my called DB schema visualization, right? So in this case, I am explicitly stating things rather than learning it from the database. So I'm saying there's a contains relationship that's established between definitions and clauses, and it's a sub-property, a sub-relationship of these. And there could be more, and I could actually, I mean, we could perfectly well come to my, and maybe in my graph there's no others, but we could add other relationships saying, hey, this is also a further detailed relationship. And it's built in a taxonomy. I mean, in this case, there's a one-level taxonomy, but that's exactly what my RAG application is going to search for. It's going to go read this kind of descriptive graph, the metadata graph, that describes what am I going to find here, and it's going to build a query based on that. So that's the ontology-driven part. So it's going to go read the ontology, and based on that, it's going to generate the relevant query. What that means is that the query itself is not hard-coded in my RAG application. The query is dynamically generated entirely based on what I put in my graph. So that's why my application becomes way more flexible, and I take control of its behavior from the graph, from the ontology definition. Make sense?
Yeah, it makes lots of sense. Yeah. I think that was helpful for everybody to understand that you take the graph, whatever it looks like, and you have an explanational layer basically on top of it that then a system like a LLM can understand and read and knows exactly what's individually happening in each branch. So let's say here it contains, but there could be other relationships. There could be, I guess, node labels as well and stuff like that, and that would then be helpful for the system to understand, okay, what is how the graph basically is connected, what the individual parts of the graph are, and how it then can interpret that and make
Exactly.
work with
And
it.
this is exactly what we did. I mean, it's sometimes it's called like a semantic layer, like a description, a semantic description of what's in the data that can be consumed by any application. And if you go, any of the people attending want to go look at episode 15, we did exactly that. So we created the definition, and then my Streamlit application would go read the ontology and dynamically generate the queries that would consume. And it's also a way of defining views over your data, because maybe you want to expose part of it and not all. And maybe you, instead of having an application that behaves dynamically based on the ontology, you want to do some reasoning. And the reasoning, and we did that also in episode, I believe it was 4, you probably remember, Alex, where we expressed something like a director or what was it, or an artist is someone who performs in a play, right? So we defined the notion of artist, and then because you performed or I performed in going meta, we were tagged, we were marked in the graph as artist or whatever. So basically, some behavior is dynamically driven based on what our definition is in the ontology. So this approach of formally putting some meaning, some semantics explicit in the graph, and having some software in the more general term. It can be a RAG, it can be a Streamlit app, it can be a reasoner that does something based on that, is this idea of the explicit semantics of the semantic layer, or however we want to call it.
Yeah. Cool.
So if we go back to the whole reason why we've done this is because now we can go back to our RAG application, and this is looking exactly for that. So we know how ontologies look like. I mean, the subproperty of relationship. And let me go down here. I think I've run this code, but you will see how we can test. So there's two types of queries: further detail, or the other one, which is inverse contextualizing. So if I run this query now, you see that it's generating something that contains the relationship contains. Why? Because it's gone to the ontology, it's read that contains is a further detail type relationship, and it's found it and populates the graph like that. Just to show very quickly how this is dynamic. You'd like to reload? Yes, let's do that. I created, this. So let's say I'm going to create another one. Let's say there's another relationship it doesn't exist in the graph, right? Hang on, not this. I'm going to use this. Another relationship. It's non-existent. It's just so that you can see how the query is built dynamically. Let's say includes. Let's say that there's another portion in the graph in the legislation that something includes something that's also there. So I'm annotating it also as a further detailed relationship, right? In this case, I'm not even specifying the domain and range. So I'm going to do this, and I'm going to save it. So if I save it, I will have my ontology here. I have to reopen it because the text editor doesn't get the refresh. So if I open with text edit, there we go. Let's make it a bit bigger. We see that now there's contains and there's includes, right? So if I take again the whole content and do exactly what we did before, if we, not here, but here. So if I go to my ontology import and replace the previous one with this new version, and I'm doing a quick and dirty copy paste. Now it's 8 instead of 6 as we saw before. So if I rerun this, bang, now we have 2. We have includes and contains. Okay. So we have 2 relationships that I can use in my RAG application to do further detail expansion, right? So if I go back to my my notebook, look at this query. Before it was just contains. If I rerun it now, it's finding includes and contains because it's found 2 types of relationships that are worth exploring. So this is entirely dynamic. The moment you change things on your graph, the behavior of your RAG application is going to change. Why? Because you're being explicit and saying this relationship has this behavior. And this sort of engine, if you want, reasoning engine, whatever you want to call it, interprets that as this is the way you want to use it. So long explanation, I'm conscious of time, but basically what I'm doing here in this step is If I run it, I'm going to basically create a contextualized vector index handler, basically on a dynamically generated Cypher query. So what happens if I ask the question now, and everything goes well as expected? Look at that. So now the result from scanning is not fragments, it's getting the whole package. It's getting an unavailable deposit, is and it has the 3 sub clauses. So it's bundling it all together.
Yeah.
Basically, it's running this query that I showed you. So when we have a node resulting that contains or includes something, take these. This query is entirely generic. So it's taking all the properties in the node and generating them. So I don't care what's there. It's entirely dynamic. That's the whole point. And returns these results. So this is what this is returning. So we have all the information. And if I pass that, if I build another Q&A chain on this contextualized handler, it's now going to produce, hopefully, a much richer definition of what an unavailable deposit is. There you go. So now we have an unavailable deposit is blah, 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 and it has a totally accurate description. 1, 2, 3. So I've made sure that the LLM gets all the relevant context in perfectly bundled so that it can generate a rich response that's accurate and complete, right?
Yeah, super cool.
This is one pattern, but like I mentioned before, we have other examples when it goes the other way. And here, the sky is the limit. I mean, you decide which are your patterns and what's the best way to chunk your document. So that's what I came up with these 2 ideas. So there was the other pattern where I was talking about reverse contextualizing. So it's kind of the opposite. Instead of getting a definition and adding all these children, I'm doing the parent approach. And that's the other idea. So let's say that in my ontology, and I'm going to do this quickly. Let's say, yes, I'm going to create, indicate that contains, it's actually not only a further detailed relationship, but it's also of the other type. It's a contextualizing relationship. So I can use it to navigate the other way. So if I persist that, and it was file save, and I reopen my document, open with all the text editor. There we go. Now we have, did it reopen it or contains? No, it didn't. I have to close it. I'm opening it with the text editor, which is
it doesn't
dynamic. So, oops.
So now it basically looks both ways.
Exactly. So, now it's defined. I mean, we can choose how to, this is too small. Let's make it a bit bigger. But you see that contains now is defined as both a property of further detail, but it's also inverse contextualizing. So it's a relationship that I can navigate in both directions, right? So again, let me do it. I'm doing this manually. Of course, this will be part of an automated kind of ETL chain of some sort. But anyway, for this session, I think it's good to do it like that. I'm literally copy pasting again. Now the newer version of the ontology, boom. Now it has another one. And if I rerun this query, now we have, there you go. So we have further detail, and contains is both further detail, but also inverse context, right?
Nice, yeah.
So again, I'm enriching the ontology. I keep adding elements. And remember that contains also had the domain and range, right? So there's additional elements. So I can keep adding explicit fragments of knowledge to my semantic layer, to my ontology, and that will further drive the behavior of my RAG application. So if I go down here now, I'm going to do something similar. So instead of this pattern, I'm going to use the other one. And of course, you will be wanting to use both in combination. Here, I'm using them separately. But let me create another one. Basically, this is the opposite, right? So if you get a detailed fragment, it will navigate to the parent. It's the parent template. And for that, I'm going to use a different query. Sorry, I'm accelerating a little bit in the interest of time. But for example, what definition mentions Section 17 of the Building Societies Act? Boom, just one question. So if I run this question, look at this. So like we did before, you will get vectors that closely relate to this one. For example, there's the building society, there's the section 17, there's a 17 here. I don't know if that's the reason why it brings it up. So there's things that are similar to it, but again, they might be, they're probably being used in isolation. So there you go, section 17 of, so this is probably the best and the right match, but it's incomplete, right? Because it's a clause of a bigger definition. And what I'm interested in, what I'm asking actually, is what definition mentions that, because I don't know. And if I get only that, and I build the RAG based on this fragmented information, it's going to tell me that the definition is the definition of a building society under clause B, which is incomplete, right? Because let's see what it's like. Actually, let me. How can I do that? So I can search for a clause, as we saw that. Let me see. That's clause where the definition starts with, in the case of a building society. Let's write a quick cipher here. So if I'm looking for a clause where and dot definition starts with something like that. So if I run that, there you go. So we get these. Why is it so big? So we get the clause, but if I expand it, I'll probably get what I'm after. So this is contained in the definition of definition embedding the term authorized. So what's an authorized? I don't know, whatever authorized means in this context in relation to accredited institution. So in the definition of authorized, if I expand it, we have a mention of these regulation, section 17 of the building societies. So what I'm after really is this definition. And what it's telling me as an answer is just based on this fragment, which is incomplete, right?
Yeah.
So that's what I'm getting. Now, in this case, it's a perfect scenario for this navigating backwards. I've got into something that's very detailed, and I want to put it in context by navigating to the parent. And that's what I've done here. So I've created not a further detail, but the inverse context. So if I run this, I can now, I suppose we have the question loaded. Now the context, look at that, perfect. That the defined term, so instead of getting me fragments, now it gets me the whole thing because it's applied the contextualizing query that has been generated dynamically again. So we have the defined term, which is authorized, and then the definition is all these sub nodes that we saw before. So this is much richer and much more accurate context to pass to the LLM. And if I pass it like we did before, I would expect to get a more accurate and richer. Oh, that was concise, but they're perfect, right? So it's the definition of authorized mentions that. Couldn't be clearer. So perfect answer, very short and concise, but it's there you go. So I'll stop here because I see it's the top of the hour. But I hope I know it's a pretty dense session because it's one of those where we really go meta. But people get the message. So what we're doing here is we are making the RAG part more dynamic so that it's driven from the graph side. So I decide what to put in my ontology, and that drives the behavior of my RAG. At the moment, my RAG application, as you're going to see when you have a look at it in GitHub, it only implements these two behaviors, these two patterns, the further detail and the inverse contextualizing. But you can think of adding several more. I mean, Thomas has published things like, what was it? The synthetic questions, the summary. So you can do multiple patterns and have kind of micro reasoners on the RAG side that can work on any graph. And that's the powerful thing of having it data-driven, ontology-driven, semantic layer-driven. I'll pause here and see if we have some questions because it's, like I said, I know it's been a dense one, so I'll give people a break.
No, totally. But I think it's very cool. I mean, last episode basically was already very interesting, but now basically this is making it more and more usable. And I would say, I mean, not that the other one wasn't usable, but this, the bigger your data pool is, the bigger your graph is, the more you don't want to type it in yourself. You want to have some kind of layer in between that takes some workload away from you and gives you.
It's a good point that you bring there, Alex, because some people might say, hey, I don't need that level of complexity and flexibility there. I'd rather hard code my query because it's only going to work on this graph that I'm working perfectly fine. Maybe you want to, but in a way, you're kind of reinventing the wheel every time. So having these kind of repeatable patterns that are generally useful. So this idea of navigating to the parent to contextualize or further specifying something. I mean, these are kind of, it's like you're building a library of tools that you can then reuse, and this works across graphs. I mean, one of the things that I was thinking if was maybe taking that and show how it works in a different graph. All I have to do is layer the ontology on top, and it will work exactly in the same way. It's too much for a single session, but yes, I mean, it's yet another tool for people to think, do I want to make my logic a bit more flexible, more dynamic, and drive from the ontology? Maybe not. Maybe I just happy hard coding. And some people might go down that route. So it's both are fine.
Yeah, totally. We had a couple of questions, so let's try if we can make it work. One or two actually from Alter Eagle. They say, would it make sense to track the queries being run for traceability purposes?
Absolutely, yeah. And I didn't show it, and some you're totally right. And one of the biggest problems of these RAG applications is traceability. What's going on? Because you see that in this single line of code, when you build a chain, there's a lot going on because you're going to the external store, to the graph store, you're doing a graph search, you're enriching the results, you're passing it to the LLM. So you want to really track what, and for that there are tools. For example, LangChain has can't remember the name of the tool they offer. I don't know if it's commercial or open source, but yes, I mean, you could build an element of that, some logging in the code that I've created, but there are tools that do that for you. But I totally agree. And when you're working and debugging and trying to find where things go wrong, this traceability is critical. Yeah, so spot on. I totally agree.
Cool. Then they follow up with, does it make sense to create virtual nodes from the ontology and then generate the query?
I mean, you generate virtual nodes when you kind of doing the preview, but you have to persist them at some point, because if you think of it, the RAG part will go and query that. So it the ontology has to be persisted in the Neo4j graph so that I can query it and get the description in the ontology. So the virtual node is also useful when you are kind of exploring the ontology before you import, but it has to eventually be persisted. I mean, think of this as multiple RAG applications. So you need to have it persisted and centralize it. So I don't think, unless I'm missing something, the virtual nodes, I mean, the visualization is one part, but you have to persist it eventually so that these elements, work correctly. So, Langsmith, exactly. That's thanks, Roy. So there's that's one option, but LangChain offers these tool to give you all traceability on what's going on in the chain.
Yeah. And there was one more from Skander. You created the ontology file manually. Do you think it can be generated automatically based on a document?
You can, but that's a different problem. I mean, so you can, if you give some a document to an LLM, for example, an LLM will do entity extraction and it will tell you these are the types of entities in your document. So you can generate an ontology out of unstructured data, but in this case, it's different. Here, I did want to take control of, because remember, that is driving the behavior of my RAG application. So to answer your question, you can do it, but in this case, I wanted to own that process and indicate this relationship is one that you might want to use to contextualize in one direction or the other. And I wanted to own that. So that's why I went down with the manual creation. But, yes, absolutely, that ontologies can be, I mean, they're always going to be halfway between the automatic generation and the curation. I mean, ontologies in a way are kind of capturing experts' knowledge. So yes, you can get help with automation, but I think it's inevitable to have some element of curation and human in the loop in that. And in this case, it made sense for us. But good question.
Yeah, thank you. There are a couple more questions. I don't know how much are we looking for time. I mean, we can go over them briefly, but because we already over, maybe we briefly touched them. One is, do you have ontology templates examples in Neo4j? So that's more like a general question, I guess, not necessarily tied to
not
today's
really.
session.
I mean, we have created in this series a bunch of them, and you will find references to them, and we publish them normally in this URL that we use today.
Yep.
But they're not really. I mean, other than in our collection of assets of the Going Meta series, they're not very well documented. I mean, they just mentioned. So, I mean, the quick answer is no, we don't. Maybe that would be an interesting thing too. But yeah, given unlimited time, that would be something.
yeah.
So
It's
we know that's something.
it's
I mean, we don't have one. You will find some examples in the series, but
maybe in the life sciences space there is BioCipher, which is kind of going in that direction. So I mean, that could be helpful, but there are as many ontologies and semantic descriptions of as many topics in the world you could think of. So it's a tricky thing. Okay, cool. And the other question, just to close it down, was from Viditya, and they say, would I be able to compare two versions of a document that has changed over time using Neo4j? Also more generic than
I would say that's
today.
That's a slightly different type of problem. Here we assume that we didn't even touch on the versioning, on the tracking changes. I would say there is an episode where we did ontology versioning. So I would recommend you have a look at that. It's just part of it. But so yes, the answer is yes, you can do it. You have to define the scope, the depth of the change tracking that you want to build in the graph. But yeah, we didn't do it in this episode. Maybe have a look at this ontology versioning episode, and that can get you maybe started.
Yeah. One more, I think, because it's interesting one, is from Angel. Tell me if I got it right. You query the ontology to get the extended cipher queries. Have you tried to use the LLM to take the LLM to use the ontology to query the graph directly?
So have I tried to have the LLM use the ontology to query? I mean, but how do you? I mean, you mean probably pass the ontology to the LLM. I mean, the thing is, the LLM is a passive element, so you can ask. I mean, the LLM is not going to go query. I suppose I suppose there are different patterns here. I mean, the short answer is in this case we were looking at this particular pattern where we have some context and some structure in the graph that we want to leverage as part of this kind of advanced RAG pattern. But I suppose you could pass the ontology and context and have the LLM generate a query, if that's what you mean. I mean, that's something that we've done, and that's exactly what LangChain, because one of the capabilities of LangChain is the generation of cipher, and it does something very similar. It will go query the graph, it will introspect the schema elements, and based on that, it will generate queries from natural language. But that's yet another pattern, interaction pattern, right? So that's where you want to, you're not doing this approach of vector search and further enrichment. You're trying to generate cipher and return results. So that's possible, but different type of scenario.
Different, yeah. Okay, cool. I think we close it for today. Thank you, everybody, for your questions. If we couldn't get to yours, sorry for that, but you can always reach out on the Discord forum of Neo4j, or Discord server rather, the community forum as well, and on our various other outlets where you can interact with us, ask questions, and you should be able to find somebody from the community to help you out or to discuss further things. Would be always interesting to hear your questions, hear your thoughts. So if you have any other points, use the YouTube comment section, also a good one for feedback, for inspirational ideas you have. If you try this out yourself, if you want to give us feedback, then use this outlet for that. Let us know if you are struggling with something, or if you tried something and had a good result with it, then obviously we would like to hear that as well. Always nice if these, we show you a little bit how it could be done, but it's just the a teaser sort of, or an inspiration for you to see what's possible. If you then take one of these episodes and build something out of it, and make it work in a full scale or proper application scenario, then that would be great to hear, because that's helpful for us to see that this is something that people actually take on in a daily life scenario. And yeah, I think we are at the end. The next session that's coming up is obviously in February. So next Going Meta is in February. Next Tuesday, though, we'll be back with another Neo4j live session. And on Tuesday, we discuss unique graph use cases for reducing risk and improved bottom line. So it's more like a bit more classical graph database technology session, but it should be interesting. Some learnings there, some good feedback, some good use cases of how to use graph databases and where to use them. So looking forward to this one. And yeah, thank you all for watching. Thank you for sticking around. And again, happy 2024, and see you soon.
See you. Thank you.
Thank you. Take care. Bye-bye.